Okay, let's see. We're working on section 9.2, Intro to Series. Sorry, my voice is a little froggy today. Um, and this one is going to focus on nth term test, harmonic series, and telescoping series. So just let's get started. Given some series, and we can show that by showing the summation of a sequence term, a sub n, if the limit as n goes to infinity of a sub n does not equal 0, then this series will diverge. And, if you just stop and think about that for a moment, if I have some series like n squared over 3n, and I want to know if that's going to converge or diverge, well, if I just take a look at the limit as we go out to infinity, so think about this term being far to the right and allow n to go to infinity, well, we can see that n on top is going to overpower n squared on top is going to overpower n on the bottom and head to infinity. It's never going to reach 0. Therefore, the sum of all these terms will continue to get larger and larger as well. So the nth term test is a very easy test to apply and should make some logical sense if you just think about it. Conversely, if I just consider the limit of a sub n as n goes to infinity equaling 0, then the test is inconclusive, meaning we can't tell whether it's going to converge or diverge. What we'll need to do is consider other tests to determine diverge or converge. So if it's not equal to 0, it's awesome. You want to do this test first. You can see what a quick and easy test it is. So do it first. If it happens to not equal 0, you're done. It's divergent. So it can save you a lot of time. Determine whether the following series converge or diverge. If they converge, find their sum. So what we're going to do is we're going to apply the nth term test. And for that, we can see above that we must look at the limit as n goes to infinity of our series 2n plus 3 over 3n minus 5. So the rule of sequence, when I look at this one, I know how to take the limit as something goes to infinity. I can play kind of the shortcut rule and focus in on the two major players from the numerator and the denominator. In this case, we can see that it is going to go to 2/3, which happens not to be 0. So, so this series, and I'm going to write, so S will diverge by the nth term test. On the AP exam, if it isn't a free response, typically you're going to have to cite which test you used to determine whether it was converging or diverging. And so with all the work we've shown there, it's easy to conclude that that series diverged. Over to B, let's apply the nth term test. So we're going to look at the limit as n gets large. And I have n factorial over 2n factorial. I really could stop there. That's what I'm going to look at. But we want to write what the rule of sequence was. This plus 1 is insignificant. And so I'm really focusing in on n factorial over 2. And in a sense, that sort of divides into and makes 1. So my answer to this question is going to be 1/2, which of course is not equal to 0. So by the nth term test, let's call this S, my series, will diverge. Take a look at C. I think you can see the limit as n goes to infinity of 3 to the n minus 2 over 3 to the n. That's going to equal 1. Not a big player here, and I get 3n over 3n, gives me 1. And of course, that's not equal to 0. So by the nth term test, our series, the sum of that series, will diverge. The next one is a little bit interesting, isn't it? If we look at the limit as n goes to infinity, we have 1 over 1.1. And I could put raised to the power n there, couldn't I? Since the denominator is larger than the numerator, the denominator is going to grow more quickly, extending the nth term to 0. And now we get this 0 for our limit, and that means that no determination can be made from the nth term test. So no determination can be made from the nth term test. And if that's the case, then what we need to do is go on and select a different test. Right now our test selection is rather limited, but I think if you looked at this, you would realize that this is a geometric series where r is equal to 1 over 1.1. So we can say the absolute value of r is definitely less than 1. And therefore, by the geometric series test, our series will converge. And then we were supposed to find the sum of this since it was converging. So let's go in and figure out the sum of this. We know that r, I'm just going to go ahead and clear the board. We know that r, absolute value of r, was equal to 1 over 1.1 absolute valued. And the sum of a geometric series goes the a sub first, or the initial term, in our case it'll be a sub 2, won't it, over 1 minus r will give us the sum. So we need to do is calculate what our first term is, and that first term will be 1 over 1.1 raised to the second. Raised to the second from that n, divided by 1 minus 1.1. And if you do the work on this particular one, I worked in fractions originally. I got 100 divided by 11. Okay. So on the next series, topic 4 is the telescoping series. And you're probably thinking, well, a telescope, I can look at the stars with this telescope. How can it be useful in Calc 2? Well, telescoping can also be thought of like the old mariners telescope that they would use. And remember how that telescope would pull apart and extend. Well, the idea is with telescoping, it's a collapsing activity. So, or like a radio antenna, it telescopes in and out. So a series such as what I'm showing here is called a telescoping series because it collapses to one term or maybe just a few terms. If the series collapses to a finite sum, then the series will converge by the telescoping series test. It's not always easy to spot the telescoping functions, and sometimes we'll need to use our technique of partial fractions. Typically, a sum can be found for these telescoping series. Let's go back up to part A here. You'll notice I have a minus 1/2 with a positive 1/2. That would sum to 0. And a negative 1/3 with a positive 1/3, which would sum to 0. And a negative 1/4 plus a positive 1/4, and so on down the line. And we also notice that our terms are getting much smaller as we go to the right. So eventually I get 1 over n out here, and that's, may not cancel, but it's going to be very, very close to 0, such that the sum of this is equal to 1 for that particular series. So it collapses. All of these terms to the right of 1 disappear because they're adding up to make 0. For telescoping series, this makes it pretty easy to spot. I wouldn't assume initially that that's going to telescope. What I would do is write the first few terms out on it. So we've got n starting with 1. It's going to be 1 over 2 plus 1, or 1/3, minus 1 over 2 plus 3 will give me 1/5. Often, like an example above, I like to put them in parentheses. It just makes it a little bit easier to track, what n value I'm on and what's happening. Now we move on to letting n equal 2. And with that, we're summing it, so we have a plus sign in between. And we put in 2, we'll have 1 over 5 minus 1 over, put in 2, 4 plus 3 is 7, so we get 1/7. And then plus, move on, let n equal 3. 3 times 2 is 6. 6 plus 1 is 7, so this is 1/7. Minus, put in 3, we're at 6. 6 plus 3 is 9, 1/9. And I think I can pick up the pattern of what is going on here, right? It's a bunch of odd numbers, and then dot, dot, dot. Eventually we have 1 over 2n plus 1 minus 1 over 2n plus 3, and this last term is going to be so insignificant. All right, so -5, +5, -7th, +7th, -9th, +9th, -11th, +11th. Gone. It appears that the sum of this series is 1/3, and therefore S converges by the telescoping series test. Okay. The next one is not real apparent. However, could I try to break this thing out into 2 fractions? And for this one, you're going to rely on partial fractions, that technique of decomposing a fraction into 2 or more fractions. So we can go ahead and solve for a and b. This should take you back to that chapter of integration techniques when we did partial fractions. I'm going to go ahead and give you a and b on this one. A turned out to be 1. So I'd have 1 over n minus 1 over n plus 1. And in class, I'll show you a quick method to find those. We used a little bit longer method last fall, and I want to show you there's a little bit faster method that we can go with. If we expand this now, let's expand our series. Throwing in 1, I'd have 1 minus 1/2. Plus, throw in 2. 2, I'd have 1/2 minus 1/3. Let n equal 3. 1/3 minus 1/4. Okay, I'm picking up on the pattern, are you? And so on. Does anything cancel or add up to 0? Indeed it does. Such that the sum equals 1. Therefore, our sum is going to converge by the telescoping series test. Woo woo. Okay, I'm going to clear this so I can get to C. Finally, on C here, I'm going to have to stop. The bell's ringing, and I got first hour coming in. I'll pick up this video at example 6, letter C.